So in this video we're going to develop a formula for finding the arc length of a curve. And for the math majors, this video is going to be the most important one. Even though we're not going to use the formula, we're going to demonstrate where it comes from and why it makes sense so that it doesn't seem like it's magic. So arc length is just the measured distance as you move around the curve. How long is the arc if you could take a tape measure and fit that tape measure to the curve and get a measurement on it? And the idea is that without a technique to measure arc length, the process that we would have to do to find arc length, if we're working from a formulaic perspective, would be to estimate the arc length. And the way that you do it, if you're interested in the arc length over a specific interval, let's say from x naught to x sub 5. So we don't know what these x values are. Some arbitrary interval from x naught to x sub 5. So what we could do is choose to cut the interval up into equal size pieces. So in this case I've cut the interval into 5 equal size pieces. And the way that we could figure out or determine the length of each of these sub-intervals that we've cut this interval along the x-axis into would just be to take the last number on the interval, the x sub 5, whatever it happens to be, and subtract the x naught from it. And the moment you do the first number on a closed interval minus the last number on the closed interval, it gives you the length of the entire line segment over which you're working. And then these sub-intervals would be, you would just take x sub 5 minus x naught and you would divide it by n, where n is the number of sub-intervals you've cut it into. So in this particular case I've cut it into n equals 5 sub-intervals. So if we did x sub 5 minus x naught and then divided by 5, we would have the exact distance between each of the x sub i's here. And this of course is a delta x, a change in x along the x-axis. So delta x, the change in x, or the width, delta x is just the width of this little subinterval, it's just x sub 5 minus x naught over n. So you break it into 5 subintervals, and to estimate the arc length of the curve over this interval on the x-axis, all we need to do is plot the points that correspond to the way that we've chunked the x-axis, and then you draw the line segment between the points. And if you could find the length of the line segment, then you could use the line segment as an estimate for the length of the curve. And of course, the smaller and smaller you make delta x, the better these line segments will fit the curve. And the idea will be to let delta x go to 0 so that we have infinitely many sub-intervals on the interval from x naught to x sub 5. So the next thing we want to recognize is that each of these line segments is going to correspond to, if we construct a right triangle, it's going to correspond to a delta x, which is the same for each of them. So we could construct right triangles all along here, and the width of each, or the base of each triangle, is going to be delta x. The height of each triangle is just going to be the change in y. And we could calculate the change of y by, for the ith interval, for the ith interval that we're working with, or the ith line segment. To get the change in y, all you would do is take y sub I for the ith line segment and subtract y sub I minus 1, or f of x sub I, which is the same as y sub I minus 1, and we would do f of x sub I minus 1. So this would be our delta y's. So the idea here is that for each of these right triangles, we could actually calculate the length of the line segment by using the Pythagorean theorem. We know that the hypotenuse of a right triangle is equal to the sum of the squares of the legs of the right triangle. And so for the ith line segment, the length of that line segment is just going to be, from the Pythagorean theorem, the square root of the delta x squared plus, and it's going to be the height. The heights are going to be the delta y's. So it'll be the height of the y sub ith height squared. And this just comes from the Pythagorean theorem. Length equals delta x squared plus delta y squared, and then length equals the square root of delta x squared plus delta y sub I squared. So this is the length of the ith line segment. And the idea is we have some number of line segments here. In my particular example, I've got 5 line segments. So I could actually estimate the arc length by adding up the length of each of the 5 line segments. So I could actually take the sum. I could say, hey, to get the estimate, so the arc length, which is customary to denote arc length S, the arc length is about, and then we could take and sum these all up. We could say, hey, take the sum from the first line segment to the 5th line segment. I have 1, 2, 3, 4, 5 line segments, which are hypotenae on 5 right triangles. Take each of them. Delta x is the same for each one because I've chunked things evenly. And then the y sub I subscript it because those heights, those delta y's, are changing as I move along the curve. And this would then give me the sum of each of the hypotenae. There's 5 of them. And that would give me a nice estimate for the area under the curve. And we could do a little manipulation with this. We could say, hey, let's manipulate this into a slightly different form. And we're going to do this because it's going to turn out to be useful. So I could say, hey, I'm going to multiply this quantity underneath the square root by 1, because multiplying by 1 won't change the value, but I'm going to write 1 in a very specific way. I'm going to write it as delta x squared over delta x squared. So this is just equal to 1, and it's all underneath the square root sign. And then once we do this, we could distribute the delta x squared in the denominator position into the parentheses. And so that would give us the sum from I equal 1 to 5 of the square root. And we would have delta x squared over, in the parentheses, delta x squared, distributing this into the parentheses, plus we would have delta y sub I squared over delta x squared. And we could leave the 1 in the numerator position outside the parentheses. And then note, if you do that, because this is a product, delta x squared times the stuff in the parentheses, we could actually simplify by taking the square root of delta x squared. And delta x is positive because it's just a distance, so I don't have to worry about absolute values. So we could write my radical bar a little bit better. So that's going to simplify to just delta x. The square root of delta x squared is just delta x, and this one goes in underneath. And then this can simplify a little bit. Delta x squared over delta x squared is 1, plus, then we have delta y sub I squared over delta x squared times delta x, and we're taking the sum of this mess. That's a horrible summation. We're taking the sum of this mess from I equals 1 to 5. And this is going to be the arc length. So the idea here is, what if we want to improve the estimate for the arc length? Well, the way that you would improve the estimate for the arc length would be to not run for exactly 5 equal sized chunks, but do n equal sized chunks. Say I'm going to do n of these. I'm going to divide by n, and then I can make n bigger and bigger and bigger, because the bigger n is, the smaller each of these intervals is. So for example, if we do n equal to 5, n equal to 10, for example, then delta x would be even smaller. Delta x would double the number of subintervals we chunk the x-axis into. And the idea is we want to let n go to infinity. We want to have infinitely many equal-sized line intervals on the x-axis, so that the hypotenusae on these right triangles fit the curve better and better and better, until eventually, if we let delta x go to 0, if we let delta x go to 0 by letting n go to infinity, we will actually get the exact arc length. So that's the game that we play here. So it's going to turn out that the arc length is going to be exactly what we get if we take the limit on this summation. We take the limit as n goes to infinity, because as n goes to infinity, delta x goes to 0, and when delta x goes to 0, we rewrite it as dx, meaning that we have an infinitely thin width being measured along the x-axis. And so as we let n go to infinity, delta x goes to 0, and we can actually rewrite this as an integral. We get the integral from x naught to 5. We get the square root of 1 plus delta y over delta x. So think about delta y over delta x. Delta y over delta x. If we let delta x go to 0, that is then dy dx, or just the derivative y prime, or f prime of x. So when we take that limit as delta x goes to 0 from that difference quotient we did at the start of Calc 1, letting delta x goes to 0 gives us the derivative. Delta y over delta x becomes dy dx. So this term in here, in the limit, as we let delta x go to 0, this term here is actually the derivative being squared. So we can rewrite this. Hey, take the derivative, or y prime, and square it. And delta x, as delta x goes to 0, we call it dx. And so here you wind up with a formula. It wouldn't be to 5, it'd just be to x sub 5 over the interval. We wind up with a formula for the exact arc length. And we do that by cutting this into infinitely many smaller and smaller size chunks until the delta x's go to 0, so that these line segments in the limit exactly fit the curve. And so we summarize this way. We say, hey, we have a formula. Hey, if we have a f of x or f of y, in other words, so you can integrate with respect to the x or the y axes, and you want to integrate over some interval either on the x or the y axis from a to b, we can find the arc length of the curve by taking the square root of 1 plus the square of the derivative dx, or 1 plus the square of the derivative with respect to y dy. And the way we would get the second formula, the way we would get this formula, which is taking the arc length with respect to the y-axis, back here where we multiplied by delta x squared over delta x squared, which is a funny form of 1, we could have just as easily said this is going to be delta y squared over delta y squared. So when we distribute into the parentheses, we would get square root of delta y squared is delta y. And then in here we would have a delta y squared, and this would be a delta y squared, and delta y squared over delta y squared would make this a 1, and dx dy is actually x prime in the limit. If we take the limit as n goes to infinity, we're going to get a dy here. Delta y becomes dy, and delta x over delta y becomes x prime, which is being squared. But x prime is just another way of saying take the derivative with respect to y instead of taking it with respect to x. So anyways, this is the formula for arc length, and in the next couple videos we're going to work through some examples using the formula.